so. All right, so now here are these two problems. All right, and it's really, there's some, you might say, who cares about graph coloring? All right, there are books and books on sort of abstract problems like this. Given a graph, can you color it? Well, you know, how many of you were walking down the beach and suddenly needed to color a graph? You know, it happens, right? It happens. In fact, it certainly happens to me. You know, I'm sitting in my little inner tube and some problem like this comes to my mind and I try to work on it. And that's how I publish papers. But for the average Joe, it might not come. But this kind of problem comes up, right? And if you know this, people don't write all of these problems up. Why? Because they're a little, maybe they'll give them as examples, but they're too sort of specific. People like to write abstract questions up. And it's your job to see that they're the same. All right, so let's see how they're the same. Right? I'm going to say not only are we're doing a reduction, but really they're the same. How are they the same? Well, let's focus on the verb. Right? Over here we're trying to schedule. Here we're trying to color. So what does that mean? It means we're trying to take something and apply it to something. Right? What are we trying to apply to what? Well, we're trying to apply something to courses. We're trying to apply something to nodes. And in fact, those are the inputs. What are our input? Over here, the input are courses. Over here, the input are nodes, right? So we're going to put courses and nodes together. For every course, we'll have a node, right? And what are we trying to apply to them? We're trying to apply time slots to the courses, and we're trying to apply colors to the nodes. So for every time slot, we'll have a color. Everybody buy this? And what are our restrictions? Here we worry about conflicts. Here we're worrying about edges. Well, we'll put an edge between two nodes. What does it mean if there's an edge between the two nodes? It means that they can't be given the same color. Right? What does it mean to put an edge between two courses? It means that Jeff teaches them and they can't be given the same time slot. Right? Or you are taking them both. So don't have them be at the same time. They're both second-year requirements. Don't schedule them at the same time. Right? So you see, that's exactly what this problem is. Right? Scheduling is exactly graph coloring. And the more you study these sorts of problems, the better you are at recognizing them, and the more useful when you go out to the world and your boss gives you a new problem, you can say, you know, that really feels like graph coloring to me, and graph coloring is NP complete. So don't fire me if I can't come up with an algorithm for it. You know? You know what I'm saying? Yeah? She's not, yeah. She doesn't exist. I really wish she did.
How different would this course be if the fairy godmother existed?
I think she would give you all the solutions to the exam questions and you would all get an A+. And even better, she would give me the exam so I wouldn't have to spend all day making it up. In fact, back to artificial intelligence, what are we going to do when the computers are smarter than us? We're going to have to find something to do with our lives, right?
Is the artificial intelligence going to be like the fairy godmother, giving you a possible solution and then you check it? Or
no, because the artificial intelligence, even if it's way, way smarter than us, still won't be able to solve NP-complete problems, right? But the AI might be able to come up with a better solution than you. In which case, you'll have to find something else to do with your day. So you can still, hopefully, you'll still have the money to lay on the beach dreaming about graph coloring. Yeah. In fact, NP-complete problems are there exists the solution, right? A harder problem is for every x there exists the y, such that for every z, right? That's a harder problem. All right, how do you do a reduction? Well, you assume you have an algorithm for graph coloring. You want an algorithm for the scheduling problem. So that's the reduction, right? So how do you do it? You're given courses and conflicts. You turn them into a graph, and the K is how many conflicts you're allowed, how many colors you're allowed. And it gives you a coloring. And, oh, no, K is not how many conflicts there are. It's how many time slots you have. Right? Because it's how many colors you have. Anyway, and then you got a schedule. Right? Everybody got that? An algorithm for one gives you an algorithm for another. And that gives you that reduction. And these are equivalent because you can do the reduction in the other direction. Right? Given a graph and a K is the number of colors, you can turn it over to a bunch of courses, and they would tell you how to schedule the courses, which tells you how to color. Right? Everybody follow that? Same. All right. But there's likely not an algorithm for either.